Imagine opening a small restaurant in your neighborhood. At first, everything works perfectly. A few customers arrive, orders are prepared quickly, the kitchen runs smoothly, but suddenly your restaurant goes viral. Now, thousands of people are trying to order food at the same time. The kitchen becomes overloaded, orders slow down, customers leave, and eventually the entire system starts collapsing. This is exactly what happens to databases when applications scale. Today, we are going to understand how modern systems solve this problem using replication, read replicas, and sharding. Hi everyone, welcome to the Tech Anatomy. In this video, we'll understand how databases actually scale, not using complicated theory, but through a real-world restaurant analogy. And by the end, concepts like sharding and replication will feel obvious. Let's start with this very simple setup. Imagine this restaurant is your application and the kitchen is your database. Every single request goes through this kitchen. When customer place food orders, the kitchen processes them. When customers ask questions like what's on the menu, where is my order, do you still have pasta available, the kitchen handles those too. This is similar to traditional database setup. Every read, every write, every request handled by single database server. And initially, this works perfectly because small systems don't need complicated architectures. But problems begin when traffic increases. As more users arrive, the kitchen starts becoming a bottleneck. Too many orders, too many questions, too many requests hitting the same system. Now, here is something very important. In most real applications, read operations are far more common than writes. Think about Instagram. Millions of users are constantly scrolling feeds, opening profiles, reading comments, watching videos. Those are reads. But comparatively, very few users are actually posting content every second, which means the database spends most of its time answering questions. And eventually, one server is no longer enough. How do companies solve this? The first step is replication. Instead of relying on one kitchen, the restaurant chain opens identical branches. Same menu, same recipes, same ingredients, and one main kitchen becomes responsible for updates. Whenever something changes, every branch receives the latest information. This is database replication. One primary database and multiple replicated copies. Now the system becomes much more reliable because even if one branch fails, another branch can continue serving customers. This improves availability and fault tolerance. But replication alone doesn't fully solve scaling because customers are still constantly asking questions. So instead of disturbing the main kitchen, the restaurant introduces something smarter, a dedicated information counter. Most customers aren't changing data, they are just reading information. So the restaurant creates separate information desk. Customers asking, what's on the menu? Is my order ready? What dishes are available? Are redirected to these counters. The kitchen now focuses mainly on cooking. This is exactly how read replicas work. The primary database handles writes, while replica databases handle read requests. This dramatically reduces pressure on the main system, and this architecture works extremely well for applications with heavy read traffic. But eventually, another problem appears. What if the entire city starts using our application? Now, Even replicated kitchens are struggling. At this point, the issue is no longer reads. The issue is data size itself. And this leads us to one of the most important concept of distributed systems, sharding. At this stage, the restaurant chain has become so popular that one set of kitchen can no longer serve the entire city efficiently. So instead of storing all customers in one giant system, the city gets divided into regions. North side customers are handled by one kitchen. South side customers go to another. East and West regions have their own kitchens too. Each kitchen is now responsible for only part of the city. This is database sharding. Instead of storing all data in one massive database, the data gets partitioned across multiple databases. Each shard stores only a subset of data. This dramatically improves scalability because load is now distributed, storage is distributed, traffic is distributed, and the system can grow much more efficiently. But sharding introduces new challenges. How do you decide which customer belongs to which shard? This decision is called shard key. For example, users might be divided by region or customer ID or account ranges. But choosing a bad shard key can create uneven load. Imagine one part of city becoming massively more popular than others. Now one kitchen becomes overloaded again. This is called a hotspot problem, which means distributed systems are not just about scaling, they are also about balancing. Modern systems usually combine all these techniques together. Sharding distributes data, replication creates copies, read replicas handle read traffic, load balancers route requests, and monitoring systems continuously track performance. This is how companies like Instagram, Netflix, Amazon, and YouTube handle millions, sometimes billions of requests, not by building one infinitely powerful server, but by distributing responsibility intelligently, exactly like a well designed restaurant network. So let's quickly recap. One kitchen serving everyone, that's a single database. Creating identical branches, that's replication. Separate information counter for customer questions, those are read replicas. And dividing the city into regions with different kitchens, that's sharding. Once you start visualizing systems this way, distributed databases becomes much more easier to understand. If this video helped you finally visualize how databases scale, subscribe to the Tech Anatomy. Here we break down complex backend and distributed system concepts using real-world visual analogies. And if there is another topic you want explained this way, let me know in the comments. See you in the next one.